at the Keynote lecture by Vladimir Stanovov from Reshetnev Siberian State University of Science and Technology, Differential Evolution, Trends, Challenges, Ways to Visualize, Understand, and Improve. Just would like to say that Vladimir Stanovov, jointly with Shahnaz Ahmedova, are world champion in evolutionary optimization. At least they won the first place at the world competition of the Congress on Evolutionary Computation in this year.
Okay.
You are welcome, Vladimir.
Thank you for presenting me. I will now go on my presentation. Can you see it? Yes.
Yes, we can see and hear you.
Oh, great. Perfect. So, yes, we'll talk here about differential evolution. So, of course, there were several talks about these algorithms in previous days. Here, I would like to perform a deeper dive into what it is, how it works, and most importantly, why it works. And of course, how can we improve it? So let's first talk about some more basic things like real parameter optimization. So I guess most of those who are present in this conference, they know what it is, but anyway. So in real parameter optimization, what you have to do, you have to find the optimum and all your parameters are real. So of course, there are many methods which perform this, which can solve this type of problems. And of course, in the area of evolutionary computation, which is the one that is interesting for me, there are also quite a lot of methods, maybe even thousands of methods. However, well, not all of them are perfect, if we can say that. And real competition, recent competitions on real parameter optimization show several important things. At least for the last 5 years, the differential evolution methods and similar methods, they take leading places. And I'm not saying that it's only first place. It's also second, third, fourth, fifth, and usually so on. So it looks like it's everyone is using differential evolution now, which was not the case like 10 years ago. Of course, there are other methods like CMAES, which is covariance metric adaptation, but usually they are not as good as differential evolution. Of course, they have sometimes very good results in several cases, but in general, they are not prize-winning methods. Another area of real parameter optimization is particles optimization, or broadly said, swarm intelligence algorithms. In most cases, at least in the competitions that are organized, they usually don't take leading places. Of course, as we have shown on Tuesday already, sometimes PSO algorithms are the best. Of course, it depends on the problems, yes, that should be solved. But at least in this setup of competitions, they are usually not very good. There are a lot of other nature-inspired, or maybe not even nature, society-inspired methods and so on. And they are called with different names, but what I have observed is that very often, if you look inside the algorithm, you would see differential evolution actually. So some equations that are taken from differential evolution, even if it's called genetic algorithm, even if it is some exotic name, usually it's something with difference-based operations. So what is happening? Why it is so important? What is so special about differential evolution? Why it is so efficient? So these are the questions that we should actually consider and answer, if we can. What are the components of success of differential evolution? If we determine the components of success, what are the main challenges? Why isn't it winning always? And also, one of the main problems in evolutionary computation, what are the parameters? Is it difficult to tune them? And how do they influence the performance? Then how can we improve parameter adaptations, or do we even need them? The next question is, how do we balance exploration and exploitation? How can we achieve this balance? And what are the ways to track if we are somehow biased from the balance between exploration and exploitation? And finally, is there a way to automate the process of designing such algorithms? Because every year there are new and new algorithms, and they're all very similar and handcrafted. Can we make it automatic? So this is the list of questions that you can see that I will try to answer in this presentation. But first, let us start with the basics. So for those who know what is differential evolution, this will be just a reminder. For all the rest, well, I hope you will learn something new here. So differential evolution is population-based meta-heuristic. So it has 4 main steps: initialization, then mutation, crossover, and selection. Selection is actually replacement, but in the terms of differential evolution, it's called selection. So one of the main advantages, it is easy to implement. It's very simple. But let us start with initialization. Usually it's a simple random generating of points in the search space. Of course, it depends on the problem, but this is how it is usually done. If you have some area, you simply initialize random points. Okay, nothing very interesting here. The interesting part is the mutation. So the mutation is actually what makes the differential evolution differential. So the classical strategy, mutation strategy, is called rand1. You can see it on the slide. So we simply take one random point and add a scaled difference between 2 other points. So that's the whole idea. Very, very simple equation, but we will see how it works a little bit later. So, and here we first meet our first parameter, it's scaling factor. So how it works? As I said, we take one vector and add a scale difference between 2 other vectors in the population. Okay, this may seem strange. Why should we even do this? But it appears that depending on the distribution of points, this could be a very good idea to guide the search process. So next step is crossover. Usually relatively simple operation. So with some probability, we take a newly generated component of vector, or we don't take it, but at least one we should take. So similar to uniform crossover and differential genetic algorithm. You can see it here on the picture how it works. So the lower left part of the rectangular here and the upper left and lower right are 3 points where we can end up after mutation and crossover. Also, we should apply some boundary condition checking method. This is the way that it is usually done in differential evolution, because, well, if you just hit minimum and you set point to minimum, this is usually not a very good idea. And finally, selection. Also very simple. If our newly generated point is better, or at least as good as the previous one that we had, then we replace the solution. If it is not, we do nothing. We just forget the new solution because there is no way to add it in the population. It is worse than what we have. So this is it, the whole algorithm. in just several slides. Of course, there are modifications, and the first modifications is just modifying the mutation strategies that you can use. Here you can see several popular ones like rand2. You have two differences. Best one, you search next to the best solution. Current to rand, you have like a line connecting a random individual and current individual. You search along this line. Current to best, you search along the line between current solution and best solution. And current to p best is actually, you can converge to any of p% best solutions, which is actually one of the best strategies. I mean, current to p best. So, okay, algorithm is relatively simple, of course. I mean, the basic version, but it is not so easy to understand how it works. So, what if we will try to visualize it in some way? For example, let us do it as follows. We generate a set of random points, select some scaling factor values, and then we sample a huge amounts of points, like, for example, with rand1 strategies. Then we build a histogram and plot it and see where are the solutions that are generated by differential evolution. So in this case, I made an example with 100,000 points to get nice pictures. So let's start with something trivial. For example, we have 8 randomly sampled points and we set scaling factor to 0. So on the right, you can see a heat map, and we always end up in the same points. We're not moving anywhere. Scaling factor is 0, so no movement is happening here. Of course, there is no crossover in this case, only random difference-based mutation. But what if we increase f? We will get a picture like this. And actually, this is getting a little bit more interesting. Why? Because actually, we have a group of points around each point, which represents rotated, the same set of points, but rotated under different angles. I mean, it looks like this, yes. And it's like a copy of the same population around each point, and also rotated with different angles. So it's a set of points which depends on the original set of points. Okay, let us increase f even more. Actually, we have the same picture with f 0.3, but in this case, this looks more like randomly sampled points, yes? So no particular structure here. If we increase f even more, well, again, some random patterns, maybe we can see something here, but nothing very interesting. Okay, but this is with randomly sampled points. What if we, for example, change f to not a fixed value, but what if we will select f as a random value from 0 to 1, uniformly distributed? We will get something more interesting, like we have like stars around each point. So we have directions in which the algorithm will search. So around each point, we can see that there are such rays, and they go only in particular directions. And in other directions, they do not exist, because there is no way to get this direction with points that are currently present in the population. Okay, but you can see one important thing here. If we sample uniformly, we see that most of the points end up close to the original points, which is probably not very good. If we use, for example, normal distribution, in this case, with a mean of 0.5, we will get something more interesting. We actually search not so close to the original point, but a little bit further from them. So, okay, this looks a little bit more interesting, yes, than with fixed f values. But let's go further. Can we do something else? So here is a picture of actually a movie. Yes, a movie that shows how this heat map is changed every generation. So every generation, like 50 generations, we sample 100,000 points and build a two-dimensional histogram. So this is Rastriggin function, similar to most of you. And on the left, you can see how the points are organized. So this is rand-1 strategy, basic algorithm, no crossover at all. And on the right, on the left part, you can see that at some point, like at generation 25, the points are getting in the local optima. Of course, some of them are very close to global optima. Yes, but most of them are aligned with the points on the graph. And if you look on the right, there is something quite interesting happening. Actually, you can see the structure of the function itself. So you can see the cells, and it appears that differential evolution samples points closer to local optimum more often than between the optimums. And this is a very important finding, because actually it appears that differential, what it does, differential evolution make it so that it uses the geometry of the goal function, it uses its regular structure, and it only searches in the local optimums, which is quite an important feature. Okay, but what if we have a different function that does not have, which is, okay, maybe unimodal. So here is Rosenbrock function, and this is what happens here. Well, I hope most of you know what is Rosenbrock function, but this looks like a banana with a long valley, and you should follow this valley, and then you will find an optimum value. So what happens if we look on the left? Of course, in several first generations, it just goes down inside this valley. But then what happens? The points are aligned. They're like in one line, maybe with some curvature, yes, but they're aligned, and you can see on the right that actually the algorithm is searching along this line in which the points are organized. And this is a very important feature. So it appears that differential evolution is not caring very much about ill-conditioned functions. And it also does not care about the axis of the original search space. So it can search in diagonal if it needs to do this. If the points of the population are organized in diagonal, it will go with some angle in the search space. So these are the two main features that actually help it work very well. So, of course, we understand that one of the main problems is how can we determine the parameters of differential evolution. And the parameters, the two main, are the scaling factor and crossover rate. There are many methods to tune them, of course, and most importantly, you can see on the slide. And the shade algorithm presented in 2013 is currently one of the most used parameter adaptation methods. So it appeared to be very efficient. So let's consider how it works. Yes, and why actually, yes, one more thing. Why should we actually use parameter adaptation? Why cannot we set f to a fixed value? Well, I have shown why fixed value is not very good. It is always good to sample f value and crossover f value as well. But it appears that if we simply sample values with a mean of 0.5, actually the performance of such algorithm is not very high. So we need to tune, for example, the mean value or the location parameter of the distribution, which we'll use to sample scaling factor and crossover rate. So how shade works? It has several memory cells, and it stores the improvement values. So these successful values of F and CR, and also how big was the improvement of fitness function. So, and based on this information, the weighted mean is calculated, which will be the new value in the memory cells. So, yeah, so here, for example, you can see how shade works. So you see that there are several blue lines, several green lines. So green lines, this is because there are several memory cells for F and CR. And as you see, it's not so trivial, actually. So, for example, CR in the last case on the right goes to almost 0.9, then it goes to 0. And it appears to be a good strategy. And probably there is no way you could imagine that this is a good idea to do it like this. And here are 4 different functions and 4 different scenarios, quite different one from each other. And yeah, one important thing about shade, it also has an external archive, which is actually usually the same size of population, and it stores the solutions that were deleted from the main population. And they are also used in the mutation procedure. But we will not talk about archive in this talk very much. Next, after shade algorithm in 2013, the L shade was proposed, which simply uses linear population size reduction. So it appeared that if we decrease the population size gradually with every generation, we delete several worst individuals, it actually helps the algorithm converge better. Why? Because at the beginning, you can check larger areas of the search space, and at the end, you can converge better to the best found optimum. So very simple idea and working very well. Of course, it is possible to apply it if you know your computational resource. For example, in dynamic optimization problems, this is not the case, and you cannot use linear population size reduction. And okay, how can we improve the parameter tuning methods? As I said, shade is very popular today, and in fact, still this year, most of the competitors in the competition used some kind of shade algorithm. But it appears that we can actually improve it with one thing. So this mean, which is a weighted average, which the weights are fitness improvements and the values are either F or CR parameters. So this weighted mean that is used in shade is actually biased. So it's so-called Lemmer mean, and we can actually change it so that it will be biased more or less. So what do I mean by this? Actually, there are many ways to calculate a mean. And the one that we are used to is simply arithmetic mean. And we can get this arithmetic mean if we use Lemmer mean with parameter 1. But we can also get contraharmonic or harmonic means with different parameter values. So here on the graph, you can see that you can get from 0 to almost 1. Like from a mean from 0 to 1, yes? So classical mean is 0.5, but you can get all the range of means with the same set of values. And the idea here is that larger F and CR values could be more preferable in a long-term perspective. We will come to this a little bit later. So, but before this, just a couple of slides. In 2008, when we participated in the competition, we also added selective pressure. This is another way to improve differential evolution, because it actually, no one was actually using selection like we are used to, like tournament rank-based selection in genetic algorithms. This was not present in differential evolution. I don't know why, but incorporating this selective pressure actually helps differential evolution very much. So in 2019, I already made a talk about this. So, for example, we used a simple rank-based selection. It helped very much. But of course, this is not the focus of our current talk, so I will not say a lot about this part. So, for example, some of the initial experiments that we made with lemma mean were with CC 2017 and 2018 benchmark functions. So there are 30 functions, 51 independent runs, and different dimensions. So, of course, we use the L-shade, our modification with rank-based selection. Here you can see some of the parameters, and most important is how this lemma mean may influence the performance of the algorithm. So we tested several values, different for F and CR. So we used different means, different mean calculations for scaling factor, different mean calculation for crossover rate. So let us see what we got. So this is the average Friedman test ranks for all 30 functions, 10-dimensional 30 functions. So on the x-axis are the p-values for different for crossover rate, different p-values for crossover rate. On the y-axis, different p-values for the scaling factor. So, and you can see that actually if we set p to 1.5, we get better results, much better than 2.0, which is a recommended parameter in L-shade, and everyone is using this, p equal 2. As for crossover rate, it seems like there is no significant influence on the crossover rate. But still, 2.0 for both is a fair choice, not so bad. But what if we go to larger dimensional functions? Here's the best case is 2.5 for F and 2.25 for CR. And the standard setting is getting much worse. So here these values in the picture are actually rank values, so yellow is better. And also you see if we use 1.0, 1.0, this is standard arithmetic mean. So if we use unbiased mean, like just a simple mean, add everything together and divide by the number, this doesn't work at all. So it's like 2 times worse in algorithm performance. If we go to even larger dimension, we get PF, the best PF in 50-dimensional test functions, 3.5, and PCR 2.25, so even larger values. If we go to larger dimensional, we will get even more values. So what this means, what is the meaning of this? Perhaps the reason is that these larger biased, larger parameters of the biased lemma means they allow us to sample larger F values. And this is good in high dimensional functions because you need to have a broader search. You have a very large dimension, and maybe if you have larger F values, especially F values, then you will get better results. So here we came up with a simple heuristic rule, different values for different dimensions, and this was our original idea. But then we decided, what if we make a larger scale experiment? What if we test like p-values from 1 to 5, even for 100-dimensional functions. And we got the pictures like this. So you see in 10-dimensional case, there is no real difference between the worst case and the best case. And I remember that I just remind you that the left lower part is 1.0 is standard mean, which is absolutely bad case for calculating updated parameter values. And in 100-dimensional functions, the best case is like 4.8, 4.6 for F, and also for CR, like 3.0. So it's highly biased mean values that are actually allowing you to get better results. But this previous graph was for average in all functions. So this is, for example, for one of the functions, this is Rosenbrock function, and here the situation is different. Here, smaller means smaller values are better. If we look at some other cases, so this is some composition function, very complex one. Here's an interesting case in 100 dimensions. You can see like a narrow track. If you set p-values within this track, you get a good result. If you step outside of this narrow line, you get much worse results. So, of course, it could be very difficult to find the best values in this case. Also, we observed that if we measure the diversity of the population with larger Lemmer mean parameters, the diversity is larger, which is obvious. We sample larger F values, we get more diversity. But more important and interesting thing is that when the first clusterization of the whole population occurs. So actually, if we set larger PF values, the first cluster, the first big cluster in the population occurs much later. So the exploration stage of the search is longer in this scenario. So after this, we thought, okay, well, yes, the sampling larger F values is probably a good idea, but do we always need them? Maybe we could use smaller values at the end of the search, in the same way that we have a large population in the beginning and small population at the end. So let's do the same. Let's use large values for F and CR sampling in the beginning and small values at the end. And what we got is a significant improvement of the algorithm. So it appeared that if we for example, start with 4 for PF and PCR, or even 6, and gradually decrease these values to 1, we get improvements for up to 22 functions out of 30. So, which is a huge improvement to the standard L-shade algorithm. And also you can see that this on Friedman ranking, where we have like 50% improvement in the mean rank for these cases. So what we can say about this? From this story, we can understand one important thing. So the goal of every optimization method is to find the best possible solution at the end. But when we make parameter adaptation, we're actually distracted by the improvements. So we're chasing improvements of fitness, and this may lead us to cases when we are not thinking in advance. We are not thinking where these improvements may lead us. So it's like we're using a greedy strategy when we're trying to achieve more and more improvements in fitness values. So sometimes getting less improvements is a good idea. And this biased Lemmer mean shows this. Yes, we are not setting the memory cells to the mean value. No, we're always making larger values. And this is what actually helps us find better solutions at the end of the search. So yes, fitness improvement should guide the search, but we should not follow them blindly. We should have it in mind that our goal is not to get the best fitness improvements right now. We should get the best optimum at the end. So as an example, what if we have a simple genetic algorithm? We have tournament selection, and at the end, we estimate the improvements by tournament selection. The tournament selection is choosing, it has a high selective pressure, and it's choosing very good individuals. But as long as it is choosing good individuals, it will get even higher score, because it seems like it gives you good solutions. But actually, this is not the case. This is exactly the same situation. We are distracted by these good results of tournament selection, but actually it may not be as good as we think it is. So this is the bias in parameter adaptation that happens. So we should fight this bias somehow. One of the ways is this lemma mean. Okay, let's go to the next part. So after these experiments with visualization that I showed you in the beginning, I was thinking, what can we do to visualize the search space of parameter values? Like, what are the possible ways to do this? And the result of this was the so-called expected fitness improvement. So it's a relatively simple idea. What if we do the following? We will set as set a set of f values, and at every generation we will sample solutions with different scaling factor values, with different f, and then measure improvements. So how good will be the solutions if we use f equal to 0.2, 0.3, 0.5, 0.7, and so on. And then let us build a picture which will show us how good are particular f or maybe CR values. So this is a visualization method, and the solutions that are sampled, they are not participants of the search. So this is, of course, it uses a huge amount of calculations. Yes, and to build a good picture, we should also remember that at the beginning, the improvements are large, at the end, they're small. So in the pictures that I will show later, every column is colored differently. So we made experiments also on CEC 2017. For example, here f, the lower border of f was -2, the upper was 2, and the step was 0.01. We also made distance histograms of pairwise distances between individuals. And so this is what we got. For example, this is band cigar function. So the upper part is expected fitness improvement. So larger improvements are shown in yellow, smaller improvements are in purple. Also, the graphs are the average expected fitness improvements, EFI, best, average, and worst in the population. So you see that, for example, for this case, a good idea is just to set f to 0 or sample it close to 0, and you immediately go to the best open. But this is unimodal function, nothing interesting here. And this is with shade with round 1 strategy. What if we go to something like Rastrigan function? Here we will get a picture like this. So in the upper part, you can see that there is the same straight line close to 0. So local search is good. And as I showed before in these movies, this is because actually differential evolution only searches in the local optima of Rastrigan function. But also you can see maybe 2 lines close to f equal -1 and f equal 1. This is also interesting part. And on the distance histogram, you can see that the population is split into several subgroups. This is very well seen that they are separated by distance. Okay, if we use some other algorithm, not shade, for example, rand1, the picture is much worse. It's not clear what should the f parameters be. For example, in GDA algorithm, you can get an improvement randomly. And this is probably one of the problems of this algorithm, why it is not performing as well as shade algorithm works. And but sometimes we can get some interesting results even with JDE. So this is some hybrid function with Katsura, Ekli, Grievand, Rosenbrock, and many others. But there is important thing here. If you look closely on the upper picture, you can see that there are horizontal lines next to f equal 1, f equal -1, f equal 0.5, f equals 0.66, and so on. So a lot of horizontal lines. And on the lower part, you can see that the population is split into several groups located probably in the local minima. This happens because our function is actually repeating. So it has a repeating structure of fitness landscape. And this is why we get f values, good f values close to 1, because it actually gets us to another local optimum, which may be better, maybe worse, of course, but usually there is a chance that we will get to a better local optimum because of the structure of the fitness function. Of course, there are some more interesting cases like Rosenbrock function, where negative, this is with different strategy, of course, current to be best. Here, f close to 0.2 or 0.3 is actually a good choice. But even here, you can see that it's drifting lower and upper and lower again. But more important things happen if we use current to be best to more complicated cases. Here you can see horizontal lines very well seen close to f equal to 0.5 and 1. Why is this happening? Because with f close to 1, for example, we are actually getting close to the best, one of the best solutions. Of course, there is a good improvement there, but also close to 0.5. This is probably because we will get to some local optimum, but also here, negative f values are sometimes also good, which is not very much used in differential evolution algorithms nowadays, at least. If we get to some more complicated functions, we can see similar pictures. F equal to 0.5 and 1 are actually good improvements. But this actually doesn't mean that we should go there and use these values. Maybe, but this is what the algorithm will try to track. So these black lines are actually the actual values that were used by the algorithm. Next, some other function. This is Rosenbrock function, but with GDA algorithm, again, we have a line close to 1.0 for f. And so on. We see this every time, different types of functions, but the same picture, or at least similar picture. Of course, there are some exclusions. For example, for some complex composition functions, it may happen so that negative f values, so going opposite, away from better solutions, is the only way to get an improvement. So this is the case when we are stacking local optimum, and we should do something with this. So this might also happen. So yes, we see these parallel lines with f equal to 1, 0.5, and so on. This shows that the differential evolution is actually very, very good in structured search space. And well, it depends on the structure very much. So of course, we could use EFE in other scenarios, not only for differential evolution, because it's a general approach. We also made experiments for EFE with CR, for crossover rates, and this is also quite interesting. It's not as entertaining as for F values, but for example, for this kind of functions, higher CR values are usually better. For other cases, smaller CRs are better. Okay, some functions are separable, some are not separable. Okay, we can understand this. But there are scenarios when something weird is happening. For example, this is B-Rastringin function. So we have like two Rastringin functions sitting together. And here you can see that at the beginning, large CRs are good. Then small CRs are good. Then large are good again. Then small, then large. And it's like switching between small and large CR values. And our idea was that if we compare the average improvement and current fitness values, we can see that this switching happens when these two curves hit each other. And yes, we can observe in different types of functions. So this is also some important information that we can extract and maybe come up with some new parameter adaptation techniques. So again, here is some switching from higher to smaller, then higher, then again smaller, better CR values. And okay, some more pictures for you. And actually, we came up with a simple rule. If the average improvement is larger than the average fitness, then CR is 1. If it is smaller, then CR is 0. Very simple, maybe even stupid adaptation. But actually, when we tested it, we saw that it could be even better than the shade parameter adaptation in some cases, which is relatively strange. Yes, we have some very stupid strategy that we made just by looking at the graph, and it works. So what this means that we got some important knowledge about how we should adapt the parameters just by looking at the pictures. So in conclusion about EFE, it's relatively simple to implement, but it requires a lot of computation. However, it may help you to understand what's happening inside your algorithms and maybe propose some new ideas how to improve it. Okay, so let us say several words about some other algorithms. So there are many approaches, as I said, for parameter adaptation. So for example, JSON with a lot of rules. In this case, in that case, use these parameters or that parameters. Of course, there is our L-shade RSP that took second place in 2018. And last year, the winners was the IMODE with local search AGSK, which is a case of, this is not differential evolution, but it actually uses the same equation. This is the case when we have non-differential evolution, which is actually differential evolution. And for example, J2020, a lot of algorithms also use the JDE framework. So in this year, what we proposed is the NL-shade RSP algorithm, which has selective pressure, which has nonlinear population size reduction, and a couple more other things. So we learned that the nonlinear population size reduction may be even better than linear. Okay, and also here we used archive probability adaptation. Okay, but this is all not very interesting. The important thing is that we used some kind of parameter adaptation strategy, actually parameter control scheme, like CR is 0 for the first part of the search, and it goes from 0 to 1 linearly for the second part of the search. So we came up with this idea. We submitted the algorithm, and we actually won this year. We were very happy about this. And okay, as I said, okay, don't have much time right now, but compared to these other algorithms from last year, we get very good results. And I will just keep this. And here, this is the final result by competition organizers. Actually, we were better than the second algorithm, like by 15% at least. But what's important that part that we should still discuss is that, yes, there are a lot of algorithms, hundreds of papers on differential evolution with different parameter adaptation and so on. Of course, we could get some inspiration from, for example, visualizing algorithms, and it might help, of course. But what if we try to automate the design of heuristics? So this is so-called automatic design of algorithms, and use it for differential evolution. Of course, the problem is it is highly computational, complex approach. But we tried to do this, and we simply used different genetic programming to design new parameter adaptation techniques for differential evolution. So we use symbolic regression with this set of functions, and we performed 5 experiments. So we had 50 trees with maximum depth of 5, and 10,000 different parameter adaptation heuristics were examined in automatic way. So the inputs were the resource ratio, success ratio, and the mean values that are actually used in shade algorithms. So this heuristic could simply use the values from shade algorithm and do just nothing, but it did something interesting. So here is a comparison of the best designed heuristics for different cases. So for example, we designed heuristics for F from 0 to 1, for CR from 0 to 1, for F from -1.2 to 1.2, and also some other cases. And we actually observed that it works much, much better than the original shade parameter adaptation. And this is an interesting finding. So how were these automatically designed heuristics working? For example, here on the picture, you can see what this heuristic does. If the resource is small and the success rate is small, then CR should be 1. Otherwise, it should be 0. Or at the end of the search, it should increase from 0 to 1. If you remember, I said that we came up with almost the same handcrafted heuristics earlier. So after we submitted that result, we tried to generate heuristics, and one of the generated heuristics was doing exactly the same thing as we did by hand, which is quite an amazing thing, I believe. And how these heuristics work? Some of them are actually looking at the success rate, for example, in this case, and if the success rate is small, then crossover rate should go up. Very simple idea. But somehow nobody ever used anything like this in differential evolution, and we designed it automatically. For F, from -1.2 to 1.2, some similar strategy was also achieved. Although there were more interesting cases. For example, one of the heuristics simply followed the rule that F should be just a square root of current resource plus some additional part which depends on the success rate. So you can see the main trend of F is just a root function with some additional jumps up. Okay, and one of the heuristics that was automatically designed was very strange because it was not looking at the actual values of success rate. It was looking only at the resource. So actually it was parameter control method, automatically designed parameter control method. So F is just a square root of current resource, and CR first goes up to 1, then drops down, and then after 0.75, it just goes up again. Again, it is very similar to what we have handcrafted by ourselves. So as an algorithm, genetic programming found very similar strategies that we have created. And here you can see the slide with comparison between the NO shade RSP and all other approaches with this parameter control method, which I showed in the previous slide, and it appeared that this method is actually, it could be even better than the method that we submitted to the competition in some cases. In some cases, it is not, but in some cases, it is winning compared, especially in 10-dimensional functions. You can see that 15 wins and only 9 losses in this case. In 20-dimensional, 16 wins and 16 losses. So, okay. So, several words in conclusion. First of all, visualization is a very important part to understand the algorithms that you're working on. Try to visualize it somehow. Maybe some of the ideas that I have shown today could be used by some of you. For example, expected fitness improvement. It's very easy to implement. Of course, you have to wait. You have to make graphs to do this, but maybe it will give you some better understanding of your algorithm. And one more important thing about parameter adaptations. Well, a good performing parameter adaptation should, how should I say it, should fight against the gravity of easy fitness improvements, but it should use them as a guiding star. So it should follow these two strategies in a balance, then you will get a very good parameter adaptation strategy. And this bias in parameter adaptation always should be taken in consideration, because greediness is destructive, not only in real life, but also in parameter adaptations. And several more things, it is possible to generate this kind of parameter adaptation techniques from scratch. And we have seen that they are not looking very greedy compared to those that we usually create by hand. And in the case of genetic programming heuristics, when we make such kind of experiment, it has a life of its own. So it's creating heuristic by itself, combining something that we are not even aware of. So, and this will be probably a source of some valuable new knowledge for future development of differential evolution. So what's going to happen in the future? Of course, there is a lot to learn about optimization methods, including differential evolution. And we hope that automatic design of algorithm is something that will come to this area in the next several years. Yes, of course, it isn't possible to improve existing parameter adaptation method, but probably we could do something more. For example, automatically search for new, automatically find some new search operators, not like simple differential mutation, but maybe there is something else, even better performance than difference-based mutation, but we did not discover this yet. So as a bonus at the end of the talk, I would like to show you this slide. Actually, these expected fitness improvements, when I looked at them, I figured out that they look very much like a spectrogram. So actually, what you can do with expected fitness improvement is actually you can transform it into spectrogram and then transform a spectrogram into sound. And then you can actually listen to this, to how the parameter adaptation in your algorithm works. And not only parameter adaptation, you can actually listen to the distance histogram in your algorithm. So here is a link on the screen that you may follow and listen to how parameter adaptation in differential evolution performs. So this is some Cassini spacecraft trajectory optimization with multi-start. So thank you for your attention, and I will be glad to answer any of your questions.
Thank you very much, Vladimir. Very impressive keynote. Dear colleagues, we have 1 minute to ask questions.
may I ask question?
Yes,
Alexander
sure.
Gornov.
Sure.
And what about hybrid algorithms? If you add one iteration from gradient methods, is it a picture of results maybe such or not?
Well, if you add some like local search algorithms, for example, sequential quadratic programming, something like this, of course it will change. Of course it will change. The problem is it will be difficult to understand what caused this improvement or that improvement. Is it the advantage of differential evolution, or is it the local search that helped you achieve the results? So I didn't do this because I was interested in how differential evolution works. But of course, you can improve it with local search.
Thank you.
What about your idea to be not greedy? Local search exactly is really great. Maybe
Yes.
thanks to your idea, we shouldn't use hybrid algorithms.
Well, combining with local search, for me, actually, it always sounded like cheating a little bit. So your algorithm is not working very well. That's why you use local search to improve it. Of course, sometimes it's a good strategy. Yes, of course. Why not? But I believe that in the case of differential evolution, its search capabilities are good enough not to use this kind of approach. And maybe, I mean, if we are not following this path of combining algorithms, then maybe we will learn something more about the differential evolution itself, the basic algorithm. So when you combine something together, it's difficult to understand where is the problem exactly. Is that you combine them in the wrong way, or that your basic algorithm is not good, or that local search is not good? Hard to say.
But actually, we wouldn't like to know where is the problem. We would like to know where is the solution.
Yeah, I understand. And I mean, the problem in the algorithm, why it's not finding the solution.
Yeah, okay. Well, somebody else would like to ask? Okay, thank you very much. And Mo1, my congratulations you with World Championship.
Thank you.